You doing okay today? No? That's an honest answer. Any questions on homework? Okay, so we started chapter 3 last time, right? And the main result, the two main results from last class were that if we had a quadratic function, it could be written in two different ways, and we could go through a process to graph the quadratic function, you know, depending on what form we had, right? Okay. And then the other result was that we had used this synthetic division thing that I showed you to try and show that you could somehow factor polynomials, right? Yes? But I had told you that there was that number that we used on the outside, and I said to, you know, next class I'll show you where that number comes from, right? Okay. So let's put up the example. If someone could look in their notes. The last example that I did, who has their notes written out decently? Let me see it real quick. What was the last one? Do you mind if I flip through? Okay, x, read that out to me. X cubed plus 4x squared minus 11x minus 30. We've gone through this example, right? And we had taken the synthetic division box, and we had put our numbers in here, 1, 4, negative 11, and 30, or negative 30. And then what number did I start with? The first one I used? 3, okay, right? I said 3, and then we showed that it worked and got us a remainder of 0. So today is about where does that 3 come from? Because if we have that 3 and it works and we get 0 out here, then we saw that we could use that 3 and the numbers that remained here to factor, correct? Okay, so where does that number come from? We're going to do something called the rational 0 test. Okay, the rational 0 test. So remember what I said about that synthetic division. That if we had the 3 out here, 1, 4, negative 11, and negative 30, and this came out to be 0. Let me just put the numbers what they were here. That was it, right? So if you take the 3 here and you get 0, that was the same as saying that if you plug 3 into this, you should get 0 to come out. So when we say rational 0 test, the 0 part of this test, the word 0 comes from the fact that what we're doing is we're gonna run a test to see if we can create the zeros of some polynomial. So we're going to have to run a test to do that. And then the whole idea here of the word rational comes from the idea that this test will work as long as the numbers out here are nice rational numbers. Now, what's a rational number? Rational number is a fraction. Okay, so fractions can look like this. 1/2, right? Negative 3/5. Those are fractions. How about the number 3? Is that a fraction? Sure, it's 3 over 1, right? So if there are fractions, okay, if there are fractions, which include integers, nice numbers, that you can plug in here and get 0 to come out, if they exist, this test will work. If there are numbers that are not fractions that you plug in that give you 0, this test will not work. Now I'll show you what that means later. Just for now, I'm just trying to explain where the terminology of this test comes from. So we're hoping that there are some numbers that when we plug them in, we get 0. So let's start off the rational 0 test. The book goes through an explanation in words of what the test is and how to do it, but I think students pick it up a lot better if I just actually do it with an example. So here's what you do. You're going to look at put it in descending order, okay, make sure it's in descending order. You're going to look at the number in front of the highest term, power of x, which is 1, and the number in the back by itself, which is negative 30. Okay, those are the two numbers you're going to look at. And I'm actually going to start with negative 30. And I'm going to write down negative 30 here. Put a hole in there. I would like to know all the numbers that divide evenly into negative 30. What are all the numbers that you can divide in evenly? So does 1 go into 30? Yes, 30 times. Does negative 1 go into 30? Yes. So 1 and negative 1 both go in, right? I should have said, does 1 go in there? Yes, negative 30. Right? 1 times negative 30 would give you negative 30. And then negative 1 times positive 30 would give you negative 30. So both the positive and negative will work. Does 2 go in there?
Yes.
Yes? 2 goes in there how many times? 15. So I'm going to go through this list, and eventually, wouldn't I get to 15? And wouldn't I eventually get to 30? So when you're making this list, the way that I do it is I write them in pairs. So 1 goes in here 30 times. So I also know, I'll make my list start down here. I also know that 30 will go in there 1 time. Does that make sense? And then when I write 2, I'll say 2 and what? 15, and I'll put the 15 back here. Like this. What I'm going to do is start bringing my list together. Is everyone comfortable with the fact that we could do positive and negative? It wouldn't matter? I think this is the first Red Bull that I've ever had without alcohol in it. No, I actually never drink Red Bull. I don't know why. I was at the store. Yeah, it's been a long time since I've been one of those.
I make those drinks a lot.
Okay, what's next? What number goes into 30? 3, right? 3 goes in there. How many times? 10. So you put 3 and then you put 10 out here. And the question is, when do we stop, right? You stop when this list comes together in the middle. So does 4 go into 30? Not evenly, right? Evenly meaning 4 times a nice number doesn't give you 30. 5? 5 and what? 6. So the next number that I would look for is after 5 would be 6, right? And so I'm already there. So this is my complete list of all the factors of negative 30. Okay. Now you have to look at the number in front, which is a 1. If the number is a 1, or if the number is a negative 1, then you're done with your list. If the number here is something other than 1, we will have to address that. So for now, we're done. All right? So I'm going to say here, since we have 1x cubed, right? And since that's a 1, okay, since 1x cubed, that number in front is a 1 or a negative 1, then this list is my final list. Okay, so this list of numbers. So think about what this actually means. Remember how we did the synthetic division? I said, let's try 3, right? We said 3 worked, and I said, next class I'll tell you how to get it. Well, does 3 appear in this list? Yes, but there's a whole lot of other stuff in here too, right? There's actually, each one of these represents 2 numbers, doesn't it? So there's 2 numbers here, 4 total, 6, 8, 10, 12, 14, 16 possible numbers to try. You get that? There's 16 possible. And so what we would do now is we would go through this list until we get it to work with the synthetic division. Understand? It's a little tedious, isn't it? I mean, can you see the potential for this to kind of suck a little bit? Okay, so let's now act like we haven't done this problem, right? We've created our list. Now we come out here and we start, where do we start in the list, right? Well, my recommendation to you, the way I design my tests, is that if you write down your list like I did, and you write it from smallest number to biggest number the way I did, I promise that it's going to happen within the first 5 to 6 tries. But if you start just randomly picking numbers off the list, you may try 8 or 10 before it actually happens. So the first number I would try is 1. When I say 1, I mean I put 1 on the outside, and then I do my synthetic division. And I'm hoping for what? A 0 down here, right? I'm hoping for a 0 right here. So let's see if this works. How does this go again? Down the 1. Yes? Okay, drop down the 1, multiply, add, multiply, add, multiply, add, and so this does not work. Okay? So scratch it out, cross it out, and move on to the next number. Now the next number you should use is not 2. Now try -1. All right? So let's try -1 out here instead. We already know 3 is going to work, right? But let's just, act like we did. 1 comes down here, -1, then we get 3, and then we get -3, and then we get -14, and then we get 14, and then that does not work. So you want to get, well, I should say it this way. The synthetic division, if you had never seen this before, the whole idea behind synthetic division is to be able to do it fast, right? Because like now, we need to be able to do it multiple times very quickly, right? You can do, instead of synthetic division, there's another type of division that you may recall called long division. You all remember long division? Ever hearing about that? It's really long, and it takes a while, and it's really a clumsy thing. Long division is more powerful than this, but this is much faster. Okay? So that's why we're going to use it. So this didn't work, so we move on to what? Next number would be 2. Okay? Let's see, 1 comes down, that's 2, that's 6, multiply 12, that's 1, and then we get 2, that does not work. So we cross it out and move on to -2. So on your test, right, when you're doing this problem on your test, you're going to have I'm going to see on the test, I should see you trying and crossing things out and seeing it fail until it finally works. So now we move to what number? -2 out here. Let's see, 1 comes down, you get -2, that's 2. That's -4, that's -15, and that's what? 30, isn't it? And that gives us 0. Wait a minute, I thought 3 worked, not -2. Well, do you remember what the final answer was whenever we factored it on the previous? What was the final answer we had? It was like x minus 3, x plus 2, what? Say it again?
X plus 5.
Plus 5? That was our final answer, right? From last class? Notice what happens if I plug -2 in right here. What do you get? You get 0. So it actually would make this thing 0. Now, when I showed you last time, I picked 3 just because, just out of the air, I just pulled 3, because I knew it would work. But it turns out if we do it in the order that I'm telling you, starting from smallest to largest, we would have got the -2 to work first. Okay? So now what do we do with this? All right, what do we do with this? This is the most important part of this. If it works, then we're trying to factor this, right? You're going to take the -2 and create a factor from it, and that factor is going to be what? X plus 2, right? And we said that the reason why is because if you plug this says that if you plug -2 into the function, you get 0. That means you have to put x plus 2, the opposite of what's there here, so that if you try and plug -2 in right here, we get 0. So this will always be the opposite, right? Always the opposite. Then what do we use now? These three numbers, right? Give us the rest. And what power will it start with? What, I mean, x to the what? X squared, right? Now, I told you last time there's a couple of ways to look at, how you determine what it starts with. I said if there's two numbers, it would start with what? If there were just two numbers, we would go x and then the next one would be a number, right? If there's three numbers, I said it would be x cubed and then numbers, right? That's one way to look at it. Another way to look at it, which you might like even better, is that if you're going to do synthetic division on this, whatever the power is here, this right here will always be one less. Okay? Always. So if this started out as x to the fourth, that would be x cubed first. If that was x to the seventh, this would be x to the sixth, and then it would just keep going down. All right? So 1 degree less, degree meaning highest power. So that's a 1 in front of x squared, isn't it? Then I have what? Plus 2x. That's the 2 in front of an x, and then the x's are coming down here, minus 15. This okay? Now, we are not completely factored, because even though we're saying that this breaks down to be these two, this right here can be factored even further. So it's quadratic, right? Meaning we have x squared. There's a couple of ways we can factor quadratic. We can do the AC method, right? The AC method. Or couldn't we just do this whole process over again? Like come up with a list for this one, and then go through synthetic division on just this piece alone? Couldn't we? So if you like AC method, or if you can do that just by looking, then you do it that way. But let me show you how you can actually continue using the synthetic division to break this one down. I have good news and I have bad news. So here's where I am. Trying to break just this down. So I'm focusing all my attention on this right now. Yeah, and I'll just remember, I need, whatever happens to this, I need to tack that onto the front. So back up here, when I'm trying to factor it, so far I know this, right? And then the rest of it, I'm going to break down. Okay, so the method would be to go and make a list for this again, right? That would be a little time consuming. We'd have to look at what? The number in the back, which would be negative 15. We'd have to look at the number in the front, which would be what? 1, which means we can make that list. But it turns out that the list that you have for this is the same as the list we had earlier. Okay? So what you can do is just continue with the list that you were using, and you can pick up exactly where you left off. So where did we tried 1, it didn't work, right? We tried negative 1, it didn't work. We tried 2, it didn't work, and then we tried negative 2, and it did, right? We can pick up from there. All right? That's where we can pick up from. So what I'm going to do, tell me if this makes sense. I'm going to create a new synthetic division box and put 1, 2, negative 15. Does that make sense what I'm doing there?
Yes.
Taking just the numbers here. Now you might think, okay, the next number I should try is 3, right? Because negative 2 worked, so the next number would be 3. Little catch to it. You have to check negative 2 one more time, because you can have what's called a double root or a repeated 0. So it would be like this. What if I wrote down something that factored to be this? Right? That would have, I should have put it this way. If I plug negative 2 in here, I get 0. Right? If I plug negative 2 in here, I get 0. This is called a repeated root. So negative 2 could work twice. Does that make sense?
Yeah.
So all I'm going to do is go here. I'm just going to try negative 2, pick up where I left off, and just try this real fast. So does it work? No, right? So that doesn't work. Cross it out, move on, and now you can move on to the next number. What's the next number? 3. Are there any questions on what I'm doing here?
Yeah.
Yes? What do you got? Yes? No? Was that a yes?
Oh, no.
Okay.
Now I understand what you're saying.
This should work because it worked last class, right? 3 worked,
Yeah.
so it should work here. 1, 3, 5, 15, 0. Now I've got to erase this because I need some room. But remember, all we're working on right now is this, aren't we? This part right here, we already had. So now, let's go ahead and decipher what this is telling us. This piece right here tells us we have a factor of what? X minus 3. And then the remaining part here is two numbers. Now, the thing that we were working on was x squared, wasn't it? So what's 1 power less than x squared? Just x. So this would just be 1x, so just x, and then plus 5. And that was the piece that I needed to tack onto this, right? So I just throw it up here, and I'm completely done. Okay, I have factored this polynomial. What do y'all think? And it is what it is, right? Sometimes people will ask me, you know, is there a shorter way, right? Is there a shorter way? Do I really have to make that list? Is there a shorter way to do this? And the answer is, well, that is the shorter way. I mean, instead of looking at something like this and saying, I don't know, I'm just going to start guessing numbers that might work. The list at least gave us, what, 16 possibilities? It reduced it down to 16, which was good news for us. Okay. Shall we try something else? Sure. Let's try it. Not ready for that. Don't think we're ready for that one. Okay, let's try this one. See what happens. Instructions here, factors. Does everyone understand that what we're doing with this rational zero test and the synthetic division is that it's actually a totally new approach to factoring, right? It's another tool of factoring. In my opinion, it should be taught way back with AC method because it's just as useful and sometimes faster. Okay, so we're going to factor this. So what are the steps of factoring? GCF, right? That's our first thing we always look for. Do we have a GCF? Nope. Okay, count the terms. How many terms do we have? 5. Do we have a technique when we have 5? If we had 2, we tried to look for like difference of squares, difference of cubes, sum of cubes, something like that. If we had 3, we did AC method. If we had 4, we did what? Grouping, right? We tried grouping, but there was never anything to do when we had 5. So the only way we're going to even have any hope of doing this is by using this whole rational zero test in the synthetic division. So what numbers do I look at? Well, I make sure it's in order, right? Descending order. I look at the 2 numbers are going to be 3, and then over here are 4, right? So the first number I'm going to work with is the one in the back. And I'm going to write down 4, and then I'm going to list out all its factors. So what numbers go into 4? 1 and 4, right? So how about this? Plus or minus 1, plus or minus 4. What else goes into 4? 2? 2 and 2, right? So 2 and 2. So I don't want to write 2 twice. Anything else? That's it, right? 2 and 2. So that's it. Now notice we have something other than 1 out here this time, right? If we have something other than 1, we actually have to make a list off of that one also. So it kind of sucks, but we need to. So I write down the other number, which is 3. And the only numbers that go into 3 evenly are what? 1 and 3 itself, right? Okay, everyone see we did not have this happen last time, right? We had a 1 out here, so we just said this is our list. But if you have something other than 1, I'm going to have to create a new final list. And here's how it works. My final list I'm going to explain it in words, but when I say it in words, it's probably not going to make a whole lot of sense. So I think it's better if you just see it. You're going to take all the possible factors of 4 and divide them by all the possible factors of 3. Other way of saying it, you're going to take this number here, this number here, this number here, each one of them individually. You're going to do this number divided by 1, 2 divided by 1, 4 divided by 1. All right? So what's 1 divided by 1? 1. So, and I put plus or minus again because I could have both positive and negative. 2 divided by 1 is 2. 4 divided by 1 is 4. But then I have to do every number here divided by the next number in that list. So now I have what? 1 divided by 3 is 1/3, right? So I have plus or minus 1/3. Then I have 2 divided by 3, which would be plus or minus 2/3. And then finally, 4 divided by 3, which would be plus or minus 4/3. Do you see the difference? Now, do you see why when it's a 1, we just say it's this list? Because if that's just a 1, then it's just that list divided by 1, which is itself, isn't it? So that's why we didn't look at it this way when it was just a 1 up there. But if it's other than 1, you have to list it out. Imagine if this number had like 6 numbers in it, right? 6 in this list, and you had like 10 in this list. Then you have to do each one of those over this, each one of the next one. You would have like 60, maybe 70 possible things happening. It's kind of ugly. All right, so here we go. You see that? Okay, so again, on a test, if you come up, I'm checking on your test that you create the correct list. Okay, that's part of your credit is getting the list right. But once you start using the numbers for synthetic division, what we need to do is we need to, I guess I need to promise you that I'll do it a certain way. And then you promise me you'll do, pick your numbers in a certain pattern. So I said start with smallest and go to largest. Okay, do that. And then don't worry about the fractions. You would do, I promise you that it'll happen somewhere in here. Okay, the fractions, just wait on those. So those you would do after the integers. Am I making sense? Okay, so I'm going to start with 1, then -1, then 2, then -2, then 4, then -4. And if those don't work, then I would move on to 1/3 and -1/3 and 2/3 and -2/3. So let's do this. Starting with 1. Let's see, I have 3, -1, -8, 2, and 4. You know what one of the biggest mistakes I see on a test is? If I have a student who's there for like 20 minutes trying to get these numbers to work, and they come up to me during the test, and they say, none of these numbers are working. You know what the biggest mistake I see is? The student will write this down, and they'll accidentally make that an 8 or something. They'll just mess up one little sign here, and then it will never work. So be very careful on tests that you copy the problem down correctly, that you copy the coefficients correctly. Take a little extra time to do that. Any questions on those numbers? Okay, let's start with 1. Okay, 3 comes down. 3 times 1 is 3. Add down, we get 2. 1 times 2 is 2. Add down, we get -6. 1 times -6 is -6. Add down, we get -4. Is this going to work the first try? Hallelujah. We're in business, right? Okay. Now, what should we do here? What does that tell me? X minus 1 is a factor. And then, what? 3x cubed, right? Because we have a 3 here, so 3x cubed. Why is it x cubed? 1 power less than what we started with. Then what? Plus 2x squared. Then minus 6x, and then minus 4. Now remember on the last problem when we did this and it worked, what was left was a quadratic? And I said you could do AC method or maybe you could factor it in your head, right? But I showed you that you could use synthetic division again, it would work. My expectation of you as a student is that you are completely comfortable with AC method or something like it, or you can factor it in your head. And that the synthetic division would only be a backup. Once you get it to a quadratic, the AC should only be backup. I mean, synthetic should only be backup. So when we look at this here, you have to start the whole factoring process over in your head. Look at what's in here. Do you see a GCF in here? Well, there shouldn't be, because if there was, we would have pulled it out earlier. There's no GCF, right, on these? How many terms? 4. How do you factor something with 4 terms? You try grouping, right? Let's do that. We could go through the whole synthetic division again, but it's actually not going to work until we get to a fraction. So if you just do the grouping on this, it'll work pretty quick. So I'm going to do this. This is separate work. Remember, this is what we have out front right now, right? I can say that this up here is x minus 1, and now I'm working on the rest of it. The rest of it is this part. 3x squared plus 2x squared minus 6x minus 4. When we attempt to do grouping, we split it right after the second term, right? We pull a GCF out of the first. Oh, yes, thank you. Thank you, thank you. We pull a GCF out of the first two, which would be a what? Just x squared, right? Okay, what would be left if we pull an x squared? 3x plus 2. Now, over here, we need to actually match that up. We need a 3x plus 2. If this is going to work, right, we need this to be this over here. We need something out front. Negative 2? Because negative 2 times this gives us this, and luckily for us, negative 2 times 2 gives us negative 4. So the negative 2 will work. So since these two match, grouping allows me to rewrite this as 3x plus 2 in parentheses, and then what goes in the other parentheses? X squared minus 2, right? So that now can come up here, can't it? Okay, so let me write that so far. We are almost there. See, you have to ask yourself, like, when is it that you are actually done, right? And you're done factoring something when each one of these can be written, or are written as linear factors. Linear meaning power of 1 on the x. That's a linear, right? This is linear. Is this one linear? No. So I need to work on that for a second. And to do that, I have to show you something that you may or may not be comfortable with. Okay, so I'm kind of stopping this problem real quick. This is just a little side note. No. If you saw this, if someone gave you this, because you're a college algebra student, because you passed the test that we just took, you would say that's a difference of squares, right? So you would be pretty comfortable in writing this, hopefully. Or maybe now that I've written it, you're like, oh yeah, I know what you're talking about now, right? Yes? Remember that formula? The general formula we had was this: a squared minus b squared equals a plus b times a minus b. That was the difference of squares formula. What do we have up here? X squared minus 2. It kind of looks like a difference of squares, except for the fact that 2 is not a perfect square, right? So in the past, we stopped at this point because we said, 2 is not something times itself. It's not like this one was, right? 4 is 2 times 2. But you can actually write this as a difference of squares. Tell me if you believe this or not. Okay, xx is just like this, xx, isn't it? Isn't the number here 2? Isn't that just the square root of 4? Or if that was a 9, this would be a 3. Isn't 3 the square root of 9? If this was a 25, this would be 5 and 5, right? That's just the square root of 25. So if I have a 2 here, if I follow the same pattern, I should have plus and minus, but what here? The square root of 2. Is the square root of 2 a number? Sure. Well, let's see if you believe that. What would happen if I multiply this times this? X squared. I'm multiplying it out to prove to you it works. What would x times negative root 2 be? Well, negative x times root 2, right? And then you do this one times this one, which would be a positive x times root 2. I'm going to run out of space here. And then what would the last ones be? What's root 2 times root 2? Yes, root 2 times root 2 is the same as root 2 squared, which is just 2, because the root and the squared and the square root cancel, so you just get 2. So that last piece right here, and would it be positive or negative? We have plus and we have minus, right? So it would be minus 2 here. And you see that the middle ones cancel. And so you get x squared minus 2. In fact, we can do difference of squares on anything. Look, I'll show you more. Let's see if you follow this. What if I put x squared minus 11? Can you write that as a difference of squares? What would it be? X plus square root 11, x minus square root 11. That'd be it. That's it. Now, of course, if it was x squared minus 81, you could still follow this formula, right? But what is the square root of 81? 9. So that's why we write x plus 9, x minus 9. But generally speaking, it's just the square root of whatever number is there. Now that only works if it was subtraction, right? If that's a minus, that's a minus, that's a minus. If that's plus, it does not factor. All right, with all that said, let's go back to this problem and finish it off. The factorization of this polynomial will be the x plus 1 we have, or x minus 1 we have here, 3x plus 2, and then this right here is a difference of squares, x plus root 2, x minus root 2. Now each of these factors are linear, meaning power on the x's are 1s, and we are done. All right. I think it's time for you to try one. Don't you think? So I'm going to make up this problem so that it works out. I'm going to show you how I'm going to create the problem. And when I show you, you'll actually see what the answer is. But your job is going to be to use everything that I've done to try and get back to it, okay? So look, here's what the answer is going to be. X plus 2, let's say x minus 4, x plus 5, x squared. So that's what the answer is going to be at the end of this. So what I need to do is put it all together and then give that to you as the problem. So I'm going to multiply this out. This gives me x squared minus 2x minus 8. I'm going to multiply that times this, x plus 5, which gives me x cubed plus 5x squared minus 2x squared. Gotta take my time here. Minus 10x minus 8x minus 40. And then I'm going to tack an x squared onto that. So x to the 5th plus 3x to the 4th minus 18x to the 3rd minus 40x squared. The instructions here are to factor. Right? So I'll help you just with the first step, because I don't want you all to mess this part up. What is the first step to factoring everything? GCF. Is there a GCF here? X squared. So that's the first thing that comes out, x squared. And then you're left with x cubed plus 3x squared minus 18x minus 40. Right? Now this piece in the parentheses, see how you do with it. Okay? Go through the whole process, synthetic division, and see if you can get to the result that I was looking for there. You can work together, you can help each other out. Ask questions if you have them, okay? Raise your hand, I'm happy to come by and kind of point you in the right direction. If you get to a result on that, let me come by and look at your work and raise your hand. I'm going to let you finish that one up on your own, okay? We all know what the answer should be, right? Because I had started with it. Let me write down what the answer is supposed to be. Was it x? Geez. Was it plus 2?
Yes.
X minus 4 plus 5? Okay. That's what you should get at the very end. Don't forget the x squared that we pulled out in the very beginning. Don't forget that. This is your homework. Problems 41 through 59 odd, 63 through 69 odd on page 327. I'm going to try maybe, I'm going to do like one, maybe two more problems. There's something else I do want you to see, okay? So, everyone have that down? Okay. While you're writing that, I'll put the problem I'm going to do up here. All right, so I've given you a problem here. It's pretty much directly out of the book. This is number 58 out of this section. And I wanted you to see that for all the problems in there, they either put like y out here, or they put like f of x, or they call it like capital H of x, or something. They name it. They name this thing, this polynomial, as like a function. All right, so don't get confused by this. The idea in this section is still just break that side down to its factored form. That's the idea. So they put y sub 2. It's just like the second y function. That's all that means. All right, so don't get caught up on that part. So how would we do this one? You could try grouping, right? Because there's 4 terms. Well, are there any GCFs in here? No. You could try grouping. Now, I'm not going to go through it, but if you try it, it's not going to work. All right? So I create my list. So my list is going to come from the 2 numbers. Am I in descending order? Yes? Okay, so I have to check with that first. My first list is all the factors of -6. The only numbers that go into -6, or you could just say 6. You don't have to say -6. Okay? Those are the only numbers that go into 6, right? 1, 2, 3, and 6. And then we have to look at the number in front, which is a 3, unfortunately. So that means I have to create a second list, and then from that create a final list. What are the factors of 3? Just 1 and 3? My final list of course contains all the first list, right? Because it's all of those over 1. So those don't change. So 1, 2, 3, and 6. But then added to that, it's all of those numbers over what? 3. The second number in this list. So 1 over 3 would be 1/3. What's 2 over 3? Well, that's 2/3. What's 3 over 3? 1, which I already have, right? So I don't need to write it again. What's 6 over 3? 2, which I already have. So this is my final list. And I will start with 1, then move to -1, then 2, then -2, then 3, then -3, then 6, then -6. And I'm hoping for a 0 somewhere early in this process. In the synthetic, I've got 3, -14, I've got 17, I've got -6. Starting with the 1. And I'm going to double check. I have 3, I have -14, I have 17, I have -6. Make sure I didn't mess that part up. Start with 1. What comes down? 3 comes down. 1 times 3, 3. Add down -11. Multiply. -11. Add down 6. Oh yeah. Oh yeah. I'm happy, right? Happy about this. So, what goes there? X minus 1. Then 3x squared minus 11x plus 6. I have a quadratic there. I could continue with synthetic, couldn't I? But just to give us a variety of attacks here, I'm going to try and do that with AC method. if I tried AC method on that, I would have the 3 here times the 6 here, that would give me 18. And the number in the middle, negative 11. Can you think of two numbers that multiply to be 18 add up to be negative 11? Negative 9, negative 2. And then you would rewrite just these three terms, right? I'm doing kind of scratch work over here now. I would rewrite 3x squared minus 11x plus 6. I would rewrite it. Remember how we did this? We did the outside ones. We didn't touch those. 3x squared. And then over here, 6. And then we rewrote the middle one as what? Minus 9x minus 2x. Factor out what? Oh, this is a plus. Do you see 4 terms, right? So grouping. What can I factor out of the first one? 3x. We're left with x minus 3, right? What can I factor out of the next one? What do I need? You need actually a negative 2, right? Negative 2. You're left with x minus 3. And then that breaks down to be x minus 3 times 3x minus 2, right? So that would come back over here. X minus 3 times 3x minus 2. And are we done? Yes, those are all linear. So this is it. All right. Has anyone seen that movie, Her? H-E-R? Yeah. It was a beautiful story. I'm not sure what medication you need to be on, but did you like it? You did? My wife got that last night and made me watch it, and then she fell asleep 20 minutes in. You ever been in that situation before? And so I felt committed because I was like, this movie has to somehow pick up a little bit, and yeah, people have different opinions on it, but for me, it's time I can't get back. All right. I think we're ready. Do you feel like you've seen enough of that now that you're ready to see how we're going to use it? Yeah. Okay. Is that yeah or no? Yeah. All right. Let's get to our main goal here. Y'all heard that terminology, you know, sound like a broken record, right? Or what does that mean when I say I sound like a broken record? I'm repeating myself? That's starting to lose meaning, isn't it? Like, who the hell? So can I say it's like I sound like a skipping CD, or is that not even? CDs aren't, so what, I mean, digital media pretty much doesn't skip, right? Or repeat, so. Another one of those issues I don't like is anyone who uses like Microsoft Word or word processor, right? If you want to save the file, it usually has the picture of the disk, right? Or something like that. You know, have you ever seen that? The disk icon, which was like the old floppy disk. That's where you would save things to. That's kind of obsolete now, isn't it? That's a terrible picture of a floppy disk. But you know what I'm saying? What does it even mean, right? It's just that's what you do if you want to save. Polynomial functions. So, look, this is the way that the book, and don't write this down unless you want to torture yourself. This is the way the book defines a polynomial function. That's the definition of a polynomial function. Where a sub 1, or sorry, a sub 0, a sub 1, a sub 2, all the way out to a sub n are numbers, and then a sub n cannot be 0. And one more thing, n is a non-negative integer, which means that it's either 0, 1, 2, any positive integer, or 0. That's the way the book defines a polynomial function. All college algebra books will define a polynomial function in this manner. So what is this saying? All it's saying is that you've got a function where you've got a variable in it. The variable is x. That x is raised to these things, right? These powers. Those powers, it can be 0. It can be 1, 2, 3, 4, okay? As big as you want. You got to 1,000, million, doesn't matter. And so you'll have x to some power, let's say x to the 4th power. And then in front of it is what? There's an a sub n. What the hell is a sub n? Well, a sub n is a number. So you have a number in front of x to a power. And then next to it, you have a number in front of x to a power. But what's the difference between this power and this power? It's 1 less, right? So if that was 4, this is 3. And then this one would be x2, right? So the powers keep coming down. So this is like in descending order. And each one of these things in front is just a what? A number. Can these numbers in front be zeros? Yes, except which one? The first one. This is the only one that can't be 0. So that's what this says. So this is saying if you have a number in front of x to a power, and then you may or may not have other x's to lower powers, this is called a polynomial function. And the degree of this polynomial function, I'll say degree is n. The degree, what we call the degree of the polynomial, is the highest power of x that appears. Okay, so that n is the highest power that would appear there. You following me? It's a very complicated way of stating what a polynomial function is. Now, we've seen examples of this before. What about this? If I ask you to graph that, could you? What is that? It's a line, right? This is a line. But do you agree that it's a number, right, in front of x, and then a number by itself, and this has a power? Is that power a non-negative integer? Was that a 0, 1, 2, 3, or 4, 5? Right, it's a 1, right? The power comes down. I have a number in front, right? And we like to look at it like this, mx plus b. That's the way we like to look at it. So is a line a polynomial function? Yes. What's the degree of this polynomial function? It's the highest power of x that we see, so it would be 1. Okay? So a line like this is a degree 1 polynomial. What about this? I just used 3. Let me use something else. Is that a polynomial function? You have numbers in front of x's, right? Do you have a highest power of x? Yes. That power, highest power is 2, right? So this would be a degree 2 polynomial. Okay. And that's a quadratic function, isn't it? That's quadratic. That's a parabola when we graph it. So this is going to be a parabola. Now we usually write these, we like it, the form we like was this one, right? ax squared plus bx plus c. That was the form that this quadratic is written in. So with Paul, do y'all kind of understand the definition, the way it was written with all that a sub n, x to the n? They do that because when you have a polynomial, it could have 100, it could have like x to the 100th power, and the next one x to the 99, and you could have so many of them that there's no way that you could write it like this. I don't think that made any sense. Hold on. Let me try and explain without trying to confuse you more. Let's say I'm trying to do, this is second degree, right? Second degree polynomial. What if I wanted to write a third degree in a general form? Could I do this? ax cubed plus bx squared plus cx plus d. Do you agree that that's a general example of a third degree polynomial? Yeah? And then I could do maybe a fourth degree, and it would look like this. Yes? So why is it that when we get to just the general definition of any polynomial, that I use that ugly thing there that I used a second ago? The general definition was this. A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all that. Why did I do that instead of just using like a, b, c, d? It's a subtle thing, but see if anyone can pick up on it. Why not just say that a general polynomial is this? A x to the n plus b x to the n minus 1. Why not just use a, b, c, d, e, f, g?
Is it because if you run out of letters?
That's exactly right. What if the degree of your polynomial is 30? How many letters do you have in the alphabet?
26.
26, right? You're going to run out. So you cannot write it in a general form if this degree is higher than the number of letters you have. Where here, if I want to look at a 30th degree polynomial, I just write a sub 30 x to the 30 plus a sub 29 x to the 29 plus a sub 28 x to the 28. You see? I will not run out of letters because I'm using subscripts. And so I have infinitely many. That's the reason. It's not because mathematicians were sitting there going, how can we really make people hate this subject? Let's just use this notation that's just ridiculous, and people would just look at it and want to throw up and leave, right? That's not it. It's we have a finite number of letters, so we have to come up with something general. All right, let's put that all away. That's just a little random thought there. So we know what a general polynomial function looks like. Everything that we've been doing last class has been a polynomial function. So the question is, what do the graphs of these look like, right? What do they look like? So the graphs have some properties. I'm just going to say polys, okay? Graphs of polys. All polynomial functions are lines if n equals 0 or 1. What do I mean by n equals 0 or 1? N is the what? The degree. If the degree is a 0 or a 1, you're looking at a line, right? Think about it. F of x equals 2x plus 1. What's the degree of this polynomial? 1, because the highest power is 1. That's a line. What if I write this? What's the degree of this polynomial? 0, right? Because remember, this is like an x to the 0 here that we don't write. What does f of x equal 4 look like? Close, close. This is the same as y equals 4, right? Horizontal line. So it's still a line. So if the degree is 0 or 1, we're looking at a line. Now, if the degree is greater than 1, that means 2 or 3 or 4 or 5 or 6 or 7 or 8 or 10,000. You will have a smooth curve how can I say this? Smooth curve and what we call continuous. What do I mean by continuous? Well, you can draw it without lifting pencil. It won't have any jumps in it, won't have any gaps in it, won't have any breaks in it. Any polynomial that has a degree greater than 1, you can draw, it's going to be smooth, and it's going to be curved, and you can draw the whole thing without picking up your pencil. You with me? What's an example of a polynomial degree greater than 1 that we've already looked at? Shit, I forgot to press record. Oh, we are recording. What's an example of a polynomial degree greater than 1 that we've already done? That we've graphed. Parabola, right? So when we have parabolas, we already know parabolas look like this or like that, right? Those are smooth, aren't they? Those are curved, and I can draw it without picking up my pencil. So parabola is an example. What we're interested in is how do we graph polynomials that are higher degree than 2, though. What we know is that they will be smooth and they will be curved, right? Guaranteed. But here are some other properties that we need to know about polynomials. So here's what we call the left and right behavior. The left and right behavior. Now remember, I'm talking about polynomial functions right now, degree greater than 1. Right? Still degree greater than 1. If you have a polynomial function, degree greater than 1, I'll put it next to this so you understand. Then here's what I mean by left and right hand behavior. The left side of the graph does something, and the right side of the graph does something. In the middle, I don't really know yet how the middle of the graph behaves. But with all polynomial functions degree greater than 1, the left and right hands have to do one of 2 things. The left side is going to go up forever, or the left side is going to go down forever. So think of it like a parabola. The parabola is either going to go up forever, or if you flip the parabola over, it'll go down forever like this, right? All polynomial functions degree greater than 1 will do something like that on the left side, one or the other. And then on the right side, it will do the same thing. It will either go up forever, or it will go down forever. Okay? In the middle, we don't really know unless we do a little work and investigate the polynomial, which is what we'll have to do. But the left and right, we're guaranteed, looks like one of those 2 things. Understand? So here's what you could possibly have. I could have a polynomial that both ends do this, right? I can have both ends do this. I can do this. I can do this. Those are the only possibilities, right? All polynomials. Well, it turns out that there is a very easy way to determine which of these it is by just looking at the polynomial without having to do any work. And this is what's called the leading coefficient test. And that's what I'm going to show you now. So recall, that means I'm going to refer to something I've already talked about. We said that all polynomial functions look like this. And everyone got sick and didn't like it, right? That's what we said? We said that the n here was the degree of the polynomial. Right? That's the degree of the polynomial. This thing in front is a what? Right there, that thing right there, we said was a what? A number, right? And it couldn't be 0? This right here is called the leading coefficient. Now, we don't like to write leading coefficient over and over and over, so we'll just call it LC from now on. Dang, it's already time for a break almost. Well, we're past due, but we'll keep going, right? Just for a few more minutes. We need to know this in order to be able to do the test. So just so we're all on the same page when I start saying these things, like what's the degree, everyone's going to look at what the power is, right? Not just any power, but the what? the highest power. And then when I say what's the leading coefficient, you're going to look at what? The number that was in front of that highest power. Okay, so here's what the leading coefficient test is. Leading coefficient test. The leading coefficient test is best described with a table. So please draw this table. Draw a little table like this. Up on the top, put degree even. Then over here, put degree odd. On this side of the table, put LC positive, LC negative. Remember I said there were 4 possibilities, right? This, right? That's it. Well, just knowing the degree of the polynomial and knowing the leading coefficient, if you know those 2 things, you'll be able to determine which of the 4 it is. And it comes off this table. If your degree is even is what? 2, 4, 6, 8, 10, 12. If your degree is even, and the number in front of it is positive, then you're looking here in this part of the table. You're guaranteed the left side will go up, the right side will go up, and what about the middle? We won't know, okay? But what we do know is what the left and right hands are doing. What do you think happens if my degree is even, but I change the number in front to a negative? It's going to take that picture and flip it down, right? So it'll go down on the left, in the middle I don't know, and down on the right. Okay, odd degree, what are odds? 1, 3, 5, 7, 9, right? 11. If your degree is odd and your leading coefficient is positive, you will go down on the left, you will go up on the right. And what do you think happens if I change it to a negative in front? Flips this over, doesn't it? So it goes up on the left and down on the right. If you want, you can actually remember these. If you remember our toolbox functions? Remember the toolbox functions? The ones everyone's supposed to know? Look, doesn't this one look like x squared? Isn't that even power? And what's the number in front? Positive 1. And that's what a parabola looks like, right? And then what if I do negative x squared? That's an even power with a negative in front, and that's a parabola flipped over. What about this one? That looks like x cubed, doesn't it? Cubic? The cubic look like that. And if I put a negative, then it flips it over. So this part comes up and this part comes down. So you get this. These are cubes. Can we take a break? Yeah. Take a quick one. Okay, let's use this leading coefficient test real quick to take a look at a couple of problems here. Determine the left and right hand behavior. F of x equals, let's say, negative 2x to the 4th minus x squared plus 1. So what does the left side of this do? What does the right side of this do? So is it a polynomial function?
Yes.
Yes? Okay, what is the degree of this polynomial? 4. Since it's 4, we have an even degree, right? What's the leading coefficient? Negative 2. Since it has a negative leading coefficient, we come over to our chart. Degree is even leading coefficient is negative, so it should go what? Down on the left, down on the right, right? Both down. So you can just do this, okay? That's acceptable. That's it. You think you could do those? I mean,
Yeah.
I don't want to do a bunch of these. You get the idea though,
Is
right?
it question mark? Just because you don't know the vertex?
Well, we don't know anything about what's inside, okay? That's exactly what the next idea is now, okay? The leading coefficient test tells us the left and right behavior, but tells us nothing about what's happening in the middle. So our goal now is to figure out what's happening in the middle. So let's think about this. Let's just say I have a graph, right? Let's just say I have some graph, and I know that the left-hand side goes down, the right-hand side goes down. So I'm just going to do this, something like that. There are so many things that could be happening in the middle of this, right? Like, for example, it could do this. It could come up here. It could come down. It could go back up, and it could go back down like that. It could do that. Because polynomials are smooth and curved, that's smooth and curved. It could very well do that. It's not a parabola, though, right? Parabolas have to look like U's. It's not a parabola. It could have done something like this. Could have come up, come back down here, gone up, gone down, gone up, gone back down like that. It's really just dependent on what the function itself is. But notice that in this example and the one before, we have some properties, some things in here that might help us graph this. What did we have for parabolas when we were trying to graph them? What were the things that we found? Vertex, right? X and Y intercepts. We are not going to have a vertex for a parabola, though. I mean, sorry, for a polynomial. There will be no way to find that highest point, so to speak. Because look at this, you have kind of like several vertexes, if you want to call them vertexes, right? But we do have x-intercepts. We have this one, we have this one, we have this one, we have this one. We actually have 4, don't we? And we have a y-intercept right there. So the steps that I gave you to graph a parabola, if you go back and look in your notes, step 1 was, I'm talking parabolas, not polynomials. Parabola was, does it open up or down first, right? Then I said find the vertex, which was the h and the k. And then we said do a quick sketch. Do you have x-intercepts? If you had them, you found the x-intercepts. And then you found the y-intercept. And then you graphed it, right? Those were the steps. Now what we're going to have are a set of steps for graphing a general polynomial function. The first step, what do you think will be? Identify, right? Instead of up-down, you're going to be identifying this. And then, after that, you will go directly after the x-intercepts, and after that, you will go directly to the y-intercept, and then you will graph it. Okay? That's the way it's going to work. So, not ready for the steps yet. Repeated roots. Repeated roots, or what we'll call repeated zeros. Let's say I have a function f, and I've broken it down already, and I was able to determine that when you factor it, you got this. Okay? Let's just say when you factored it out, that's what we got. Then tell me where the x-intercepts on this thing are. What would make that thing 0? Here. What values of x could I plug in here and get 0?
7.
7 would give me 0? What else? Negative 3 would give me 0. What else? Negative 1 would give me 0. Right? So if I multiplied this all together, okay, if I did, I'm not going to do it, but if I did, I would have this times this would give me an x squared, wouldn't it? And I'd have to do a bunch of other stuff. But then once I got that together, I'd have an x squared here with some junk in it, right? And then that would multiply times this. So when I multiplied the x squared times x squared, or x squared times x, what would I get? X cubed, wouldn't I? So I know that if I did multiply that all out, I would get an x cubed and then plus a bunch of crap over here, right? And I don't care about that right now. Can you tell me what the left and right hand behavior of this would be? Odd power, right? Odd degree, and what's the leading coefficient? It's positive. So what happens with odd and positive? Down and up, right? From left to right, it's down and then up. So look back at this graph. If this point's on my graph, I have to go down from this point, don't I? And then over here, this is my furthest point to the right, I must go up on this side, right? Does that make sense that it would do this? The only thing left to resolve for us is what does it do in here? And I know I have to hit the x-axis here, don't I? So don't write this down, but tell me if you agree that it looks like it may do this. Yes? That seem reasonable? Smooth, curved, looks like it could do that? But is that the only thing it could do? How about this? Could it do this? I'll draw it solid this time. Is that still smooth and curved? That. Remember with parabolas, we could have the vertex just hit the x-axis? Same thing here. Could we have that polynomial just touch there and go back up? Sure. So it could do that, right? Could it do this? Could do that also, right? All these pictures look different, don't they? And we have to determine which one it is. Understand? But there's a very easy way to do it. All right? I want you to first just see that there are many different variations of what could happen. So how do we determine what happens here? Well, I said it was easy. I think it is once you see it. All you have to do to determine what happens there is look at your factored form of the polynomial, which means look at this one right there. Once you have everything factored out, right, and you write out your factors like this, you look at the power on each factor. So on this parentheses right here, what's the power out here on the parentheses? It's a 1, right? What's the power on this one? It's a 1. What's the power on this one? It's a 1. If the power on the factor, not the power in here, not the number in here, the power. If the power is odd, what you will do is at that 0, you will actually punch through the x-axis, cross through the x-axis. And if the power up here is even, you won't be allowed to cross the x-axis. You'll have to actually bounce off of it. Now, I'm going to go through more examples so you can kind of see this come to light. But look at what's happening here. What's the x-intercept that we got from this one? -1. So look, at -1, what I know, because this is odd, is that I must cross through when I get to this point. I must cross through the x-axis. When I'm at, what x-intercept is this? -3. When I'm at -3, I must cross through the x-axis. And when I'm at 7, I must cross through the x-axis again. So the only way I can draw that, do you agree if I'm going to start from down here, when I come up to this, if I have to cross through here, I have to go up?
Yes.
Right? And then I have to get back to this point. And when I get to that point, I must what? cross through again. So I must come down like this. And then when I come back, I have to get to this point, and I'm supposed to cross through here also, right? And when I go through, well, obviously it crosses through to continue, doesn't it? So this is the graph. This is it. This is what we're looking for. I'll formalize this all in one note so we can put it all together, all the ideas. I just wanted you to see with a first example. Now, I think maybe the natural question to you might be, when I draw this, right, when you're doing this for a test, how far up should I go, right? Because this would have been a correct answer also, wouldn't it? Right? So how high do you go? How low do you go? I don't care, right? I don't care. And if you wanted to know how high and how low those points were, if you actually wanted to do that, if you're interested in that, you would have to take calculus. Calculus will allow us to find the highest and lowest points on this. But we can't do it in college algebra. Okay? What's that?
Is that like the maximum?
Maximum, minimum values, yes. Yep. Have you seen derivatives in calculus? Yeah. You find where the slope of the tangent line is 0, and then you're there. Okay, so let's do another one of these before I give you the formal roots, the formal definition. Let's see, what would happen here? What if I had x plus 2 times x minus 4 times x plus 2? What if I had this? So I started out with the function, I factored it out, and I got that. So where would I have x-intercepts?
-2.
At -2, that comes from here, right? -2. And 4, which is from there. And where? -2. Wait a minute, we already have -2, right? Do you see right here we have a repeated root, which is what I was saying up here, repeated roots? What happens when we have repeated roots? Well, we need to make sure we rewrite this like this, right? Isn't x plus 2 times x plus 2 here the same as x plus 2 squared? Yes? Tell me about the left and right behavior of this function. What's the degree? What's the highest power? I mean, what's the degree and the leading coefficient going to be? So same idea. If I multiplied this times this, I would get what? X squared, and then I have a bunch of junk next to it. And then when I multiply that x squared times this one, I would get x cubed, and that would be just, what? This one? Same thing we had before? Down on the left, up on the right? So from this picture, I know that I would have to go down on the left and up on the right. But what's happening at each of these points? Let's talk about -2. Where does -2 come from? It comes from this factor right here. What's the power on that factor? 2. If that number is even, you bounce off that, or you don't cross through. Okay? You can either say you're going to bounce off of it, or you just touch it and come back. And then what happens at 4? Because that's a 1, I actually will cross through. So let me try this. I'm supposed to draw this, come up here, bounce off, so maybe something like this, right? Just don't do this. You can't go through and back down, because now you cross through, right? You just bounce off there, and then how far do I go down? Oh, it's up to me. And I try and come nice and smooth and curve back up and cross through into 4. Okay? I think it's time for a formal process of how to sketch these, right? How do you sketch these? How to sketch Pauli functions. The first step is use the LC test to find left, right behavior. Use the LC test, leading coefficient test, to determine what's happening on the left and on the right. That part should be pretty straightforward, right? Find the degree, find the leading coefficient, use the table, you're done. Okay, the next step is to find the x-intercepts. Now, to do that is going to require some work. To find x-intercepts, remember what that meant was that we set the function equal to 0, doesn't it? Isn't that what that means to find the x-intercepts? You set your function to 0. That might require that when we get our function equal to 0, that we have to do what to the function to solve this? Factor it, right? We may have to factor this. In fact, we will always have to factor it. So I'll put here in a little side note. Well, you know what? I'll just put it over here. Factor if needed. Okay, we factor if needed. Once we factor, determine the zeros and bounce or cross. When do we bounce again off of a 0 or an x-intercept? When do we bounce off of it? When the power is what? Even. When do we cross? When the power is what? Odd. And when I say power, what am I talking about? Power of the factor itself, right? The thing in parentheses. So I figure out what the left and right hand behavior are. I figure out where it crosses the x-axis. We can also find the y-intercept, right? How do you find a y-intercept? That's right. Find y-intercept. For that, all you do is plug 0 into the function. And then we do a graph. At this point, we graph it. So here's what we'll do for the graph. This step 4. I'll say sketch. In the sketch, here's the order in which you should do things. First, plot x-intercepts. Put your x-intercepts down. Next thing, plot your y-intercept. Next thing, draw your left and right behavior. What do I do after I do that? So I put all my x-intercepts down, I put my y-intercept, I draw my left and right behavior. What next? Yeah, use your cross bounce thing to draw the rest of it, right? Okay, so this is the most critical part of it. Use the bounce cross information, info, to complete the drawing. Now the book has a technical name for this whole bouncing crossing thing. You know how when I said if you take this factor and if it's raised to an even number, then you bounce, and I said if the factor is raised to an odd number, you will cross? They call that number up here the multiplicity of the root, or the multiplicity of the 0, or the multiplicity of the factor. So they say if the multiplicity is even, then you will do this, and if the multiplicity is odd, then you will do this. I just kind of threw that word out, and just in hopes that you see it more visually than trying to tie a name to it. All right? We're ready. Your next exam will consist of probably two graphings of parabolas, one or two of these, and then just one of the next type of function. That's it. It'll probably be a 5-problem test. So we are at the point of like a major idea here. You can do this, you'll be good on the test.
You ready to do this or what? You all excited?
Here we go. Let's try this. Sketch the following polynomial function. F of x equals x to the 4th minus 9x squared plus 4x plus 12. Let's go through the steps. First step is what? Determine left or right. Now, there is actually a step before this first step, which is you got to know what the hell you're looking at, right? We all have to be able to look at this and know it's a polynomial function and not a quadratic function, right? If I give you a quadratic, if this was just this, right? Then you would do the steps we did last class, which would be, does it open up or down? Find the vertex. There were 7 steps. That's what you would do. But because it's beyond quadratic, right? It's actually 4th degree, then we will treat it like a polynomial and we will use the steps I just gave you. So left and right hand behavior. What does it do? What's the degree of this? Degree is 4. What's the leading coefficient? What is it? 1. So we have an even degree. We have a positive leading coefficient. So it is what? What does it do? Up, right? Up, I don't know, up. Now on your test, if you just draw me this, I'll be happy. But this is just for the notes. I wanted everyone to understand the degree. It came from here. The leading coefficient comes from here. All right, so I know when I draw this, it goes up on the left, up on the right. Second step, and the most challenging step, are the x-intercepts. So to find the x-intercepts, I will set this thing equal to 0. I mean, set the entire function equal to 0. And I have no idea what makes this 0. The only way I could possibly know what would make that 0 is if I'm able to factor it. So I look at it, go through my routine. GCF, nope. How many terms? 4. If you try it, grouping, it will not work. Do y'all see that we actually have something kind of strange here? It goes from x to the 4th down to x squared, and so it's not even like decreasing 1 by 1. We have like a missing term in there, don't we? An x cubed term. Okay, since this does not factor with grouping, and I can't figure out any other thing to do with it, the only thing I'm left with is what? The synthetic division, which means I have to come up with my list of numbers first, create the list, then go through my synthetic division until it works, break it down, break it down, break it down, right? So here we go. So I'm going to come up with my list. Now, my list of possible candidates, because the number in front of the x to the 4th is a 1, right? Because it's a 1, I only have to look at the factors of 12, right? This was the good case. Okay, so what are the factors of 12? 1 and 12 itself, right? What else goes into 12? 2 and 6, 3 and 4. And I've met in the middle there, right? So that's it. There are, what, 1, 2, 3, 4, 5, 6, but there's 2. So there's 12 possible numbers that can work here, potentially. What next? Synthetic. Okay, write your synthetic division box down and start with 1. Or actually, you know what? Write your synthetic division box down, put a 1 out here, and then don't do anything. You got it? Let me see. Well, I mean, actually, put your numbers in them. Put the numbers in your synthetic and put a 1 out here, but don't do anything after that. Okay? I want to come around and see what you have. Oops, sorry. Okay, I only saw 4 that were correct. You see it? It goes x to the 4th, and then there's no x cubed. You do not want to make that mistake on the test, right? So it should be a 1, and then 0, then -9, then your 4, then your 12. Okay. That would have been a disaster, right? If that had happened on test, that would have been the end of it right there. Okay, start with 1. So I'm going to work through this now. 1 comes down, 1 times 1 is 1, add down 1, 1 times 1, 1, add down -8, -8, -4. It did not work for me. Does -1 work? Let's see. I don't know why I put 0, sorry. I was being hopeful. -1, -1, -1, -8, 8, 12, -12, 0. All right? Why does everyone give me a weird look? Yes or no? Yeah? No? Okay. What does that tell me so far this thing breaks down to be? X plus 1. What? X cubed minus x squared minus 8x plus 12. Okay. All right, the thing in the parentheses has to go down further, right? And grouping will not work on that. That has 4 terms in it, doesn't it? It will not work, though. So what I'm going to do is continue synthetic division. I'm going to continue in my list, and I should continue with the -1. Even though it worked, I want to try it again. So I'm going to do a new synthetic division, but I'm working with what numbers instead? 1, -1, -8, and 12. -1's not going to work, okay? I won't show it, but it's not going to work. So what would I move on to after -1? 2. I think 2 is going to work. 1 comes down, 2 goes here, it's 1. 2 goes here, it's -6. And -12 and 0. I'm happy about that. So what does that tell me? X minus 2. And then the rest of it is what? x squared plus x minus 6. Now let's kind of keep things in order here. This piece that I just got right here, that right there, is actually this, right? I still have that x plus 1 out here. So don't lose track of this stuff, okay? You'll need that. This part became this, and now I'm going to try and break this down, right? And I have options here. I could continue with the synthetic division. I could do AC method. I could just, maybe I'm at the point I can do that mentally. But can I trust that everyone can I go to the next thing without actually showing it? Y'all okay if I break down that quadratic just on my own, mentally? Okay, so I'll put dot, 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 meaning maybe it might take you a couple of steps to get to this. But this would be, what is it? Go ahead, if you've got it. Plus 3 minus 2. Plus 3 minus 2. You would have to, if you did AC method, you're trying to get negative 6 and positive 1, right? If you try negative 6 and positive 1, that doesn't add up to be 1. The only thing that'll work to mess around with the numbers a bit here is 3 negative 2. This is still that entire blue part, right? So am I all the way there? I mean, these are linear, right? I have that 1 out here. So now I'm ready for the final factorization. My f of x, which started out as that big ugly thing, has now been factored to be x plus 1 times x minus 2 times x plus 3 times x minus 2. Any questions on that at all? Good, I'm glad you saw that. So now it's being recognized that I have an x minus 2 that's there twice, so we have a repeated root or a repeated 0 or a repeated factor, however you want to say it. So, and it doesn't matter which order I put it in. I'll do the x plus 1, I'll do the x plus 3, and I'll tack the repeated root onto the end. Which now becomes enough for us to get our zeros, right? I mean, can you tell me now if f of x equals 0, if I set this equal to 0, that means I'm setting x plus 1 times x plus 3 times x minus 2 squared equal to 0. So I'm setting that equal to 0. So I set each of these equal to 0, right? Now, a lot of the times you can just look at it and see what it is, right? Negative 1, negative 3, and 2. But technically, what you're actually doing is taking that factor, setting it to 0, taking the next factor, setting it to 0, taking the next factor, setting it equal to 0. I don't have to worry about the squared, because I have 2 of these equations. They give me the same answers. Now, the only reason I'm saying that is because as I move on and do a couple more problems, it might not be as obvious. Like you might have something like 5x plus 7. And so you have to actually solve that and get negative 7/5 instead of just looking. So we have x is negative 1, x is negative 3, and x is equal to 2. Now when I get to this point, I know where my x-intercepts are, right? Go back to step 2. What did step 2 say? Find x-intercepts. Set f of x equal to 0, factor if needed, then what? Determine bounce or cross. So I have 3 points where this graph must be on the x-axis. It would be nice to know if I actually cross through there or if I bounce off. So let's go to negative 1. Negative 1 came from this factor. What is the multiplicity of that factor? It's a 1, right? That's the power on that factor. Anytime we have an odd power on the factor, it will cross through, right? I'll just put a C for cross. Negative 3 comes from the factor x plus 3. It has a multiplicity of 1. which is an odd number, so I should cross through at -3. And then 2 comes from the x minus 2 factor, which is squared, so I have an even power. Even powers on my factors tell me that I bounce. Is it all right if I use B? Okay. What are some of the mistakes I see? When people are trying to determine crossing and bouncing, they don't look up here. They'll look at the number and they say, oh, 2 is even. 3 is odd. That's not what you're looking at. You're looking at the powers. Okay? All right, what is next on our agenda here? Y-intercepts. So we're on step 3. The y-intercept should be easy to find, because all we have to do is plug 0 into the function. And because of the way the function was written out, isn't it going to be that constant that was in the back? What is it? 12? And now I'm ready for step 4, which is my sketch, right? What are the first things I should put on my graph here? The x-intercepts, which were -1, -3. So let's say that's -1, -2, -3. And then I had another one at 2. There are my x-intercepts. I have a y-intercept at 12. So remember, on the y-axis, I can count however I want. So how about I say that's 5, that's 10, so 12 would be about there. Agreed? So I've got my x-intercepts and y-intercepts. Now what? Left and right behavior. This one was what? Up, up. So what I do is I go to the point that I have furthest to the left, and from that point I know I have to go up, right? And then on the right side, I know I have to go up also. And now I just put together the bounce and cross stuff. What happens at -3? I cross. So I must come down through here, right? What happens at -1? I cross. So I have to, but look, I got to get up there, don't I?
No.
So I've got to come up here like this. And then, now does it have to be my highest point? Like, does it have to be like that? Not necessarily. And I don't really care too much, okay? If you want to make that your highest point, you can. If you want to make it go like that, that's fine. It does not matter. As long as you do go through that point, I'm happy. And then what happens? Get to 2 and I bounce. You see that you would actually have to bounce off 2 to come back up like that? When you're done with your picture, it must pass the vertical line test. Remember the test to see if something was a function? So when you're done and you step back, it can't look like this. Okay, you can't have something like that would not pass the vertical line test right there. That's it. So when I'm grading these, what I look at first thing I look at is the graph. Because normally if the graph is good, the work's good. So I look at the graph. If it's correct, I go back, I look through the work, make sure everything is good. If the graph is wrong, then I know there's mistakes somewhere, and I really have to take my time to look for them. All right, so we're graphing by hand, polynomial functions. Let's see. Can somebody, just for a couple of seconds, let's hit the light. Let's go ahead and hit them all so you can take a little power nap real quick. That's good. Have any of you ever seen this website, Wolfram Alpha? Did I show this to you? Yeah. Okay, what was the polynomial function that we had? It was x to the 4th minus 9x squared plus 4x plus 12. Okay, you see that? I just typed it in. You see how I typed it in? X raised, use the little caret key. If I go to this website, which is free, open to the entire world, if I do that, just hit enter, it will graph this for me. See that? There it is. Now, unfortunately, I don't think I can zoom in on it. I have to like buy a special access, but that's the graph. Notice what happens. The left side goes up, right side goes up. Where does it cross through the x-axis? Looks like at -3, right? Comes down, comes back up. At -1, it crosses through. It goes up, it passes through 12. Oh, we kind of got lucky. That wasn't the highest point. But it does come back down, and it comes to 2, it bounces off, and it goes back up. So the question that you might ask yourself is, well, why in the heck do we have to graph this by hand if I can just go to a website and have the graph without any work, right? I mean, just boom, it's there. And I think that's a very valid question because there's the technology that's available to students nowadays is way beyond what educators possibly thought would be possible a few years ago. So the Texas Higher Education Coordinating Board that decides what classes you need and how they're taught, I think is still a little behind with things. They still want us to teach, how this stuff is done mechanically. There is a lot of algebra in here. There's a lot of things we're doing, solving equations, factoring. These are techniques that you would need later on as engineers or something like that. But in a college algebra class where most of you are not moving on, it would be more interesting for us to spend our time talking about problems that are interesting to us, and then looking that they're modeled with polynomial functions, and then getting on here and doing our graph that way, and just spending our time doing all the math with this. Let that do the math for us, and let's answer more interesting questions. Can you please stop texting?
Yeah.
Okay. It sounds like it looks like that's enjoyable, but okay. You know what the policy is on that?
Yeah.
10 points off the exam? You don't care?
No, I do.
Oh, okay, I just want to make sure. I've seen a couple of y'all texting. I just don't want that getting out of control. All right. So I think what I'm trying to get at is that this sort of thing kind of frustrates me a little bit because it is so easy to do 20 minutes of work in like 10 seconds. But until we kind of get things lined up properly, where what we're told to teach and what we should teach are lined up, and so we can utilize this technology, unfortunately, we're going to do this by hand. Okay? All right, so we can hit the lights.
Good news is at least we can check our work, right? Pretty quick.
All right, let's look at something a little more challenging, I guess. About this. We have a function, f of x equals 2x to the 4th plus 15x cubed plus 31x squared minus 3x minus 45. This will probably be our last problem of the day. All right, quick, step 1. Left side goes up, right side up. Yes? Up, up. Two. X-intercepts. So I'm looking for the x-intercept, so I set the function equal to 0, which means I need to factor a 4th degree polynomial that has, 5 terms in it. I don't have a technique for that. I look for GCF first. Always look GCF first. I don't have one though, right? Okay, if I don't have a GCF, then I'm left with this rational zero test synthetic division, right? All the factors of 40, oh crap, I have a 2 out there also, don't I? at 45 and the 2. So I have to list out all the factors of 45, then all the factors of 2, take all the factors of 45, divide them by all the factors of 2. So my factors of 45 are less 1 and 45. What else goes into 45? 2 doesn't. 3, yeah, 3 and 15. And if you need to, just break your calculator out and just go 45 divided by 2. And if it doesn't come out, 45 divided by 3. Whatever it takes. 4 doesn't go in, 5 goes in 9 times, and 6, 7, 8, 9? 9 already, right? So that's it. That's our list. And then we go with factors of 2 are 1 and 2. So now our final list, I'll put our final list up here. Our final list will be the original list that we had for 45. And then, in addition to that, every one of these numbers divided by 2, which would give us what? 1/2, then 3/2, then 5/2. Jeez. 9/2, none of these are simplifying. 15/2, and 45/2. I will look for that list on the test. What I'm trying to tell you is that you will get credit for that. Just take the time to write it out. So we have potentially 2, 4, 6, 8, 10, 12, 13, 14, 15, 20, 24 possible candidates for synthetic division. We will start at the far left end. And I just erased that crap. And we will work as fast as possible here. We have as our numbers what? 2, 15, 31, -3, -45. Go through, double check, make sure your signs are correct, and now start your synthetic, starting with 1. Cross your fingers, pray, whatever it is that helps you get through. 48, 48, 40, oh, no way. First try? Right, first try. Now, I could rewrite everything now, couldn't I? Like, I could say this comes down and it gives me what? X plus 1, and then I can rewrite that. And then I'm going to do synthetic division again. Wouldn't you agree? Yes? It'll be, did I say X plus 1? Sorry. X minus 1 comes down, and then you rewrite the rest. But you're going to do synthetic division on those numbers again, aren't you? So here's just another kind of short option for you. If you know you're going to do synthetic division again, then why not just start it now? And the number on the outside should go, what number should you use?
1.
1 again, try it. Now, I don't think it's going to work, but I'll try it. Now, I'm going to box something up here. I'm going to circle this one because that one did work, right? So I want to make sure I don't forget that one. Okay, bring the 2 down. 2, 19, 19, what's that? 67. This isn't going to work, is it? That's not. So then, keep on going, right? I'm working with 2, 17, 48, and 45, and I try -1 now. Are there any questions as to what I'm doing here? It doesn't look good to me here. 2. Has anyone ahead of me? What do you got? What works? This one? No?
Oh, no, I did it differently.
Okay. Did you start with a different number?
Yeah, started with
Why'd you start with -3? Just out of nowhere? Okay. Just curious. All right, so has anyone tried 2 yet? No?
I got all the factors out of time.
So did 2 work or not?
2 not work.
-2?
Nope.
3 did?
-3.
-3 works? Or -3 or
Yeah.
-3? Okay, so understand we'd have to continue this, right? -1 doesn't work, then we go to 2. 2 wouldn't work, you go to -2. Then you go to 3. 3 wouldn't work, you go to -2.
Choose not.
Oh, 2's not even on there. Shit. Okay, yeah, sorry. My bad. You wouldn't use 2. You could, it would definitely not work though. Okay. So yeah, 3. I apologize. So 3 wouldn't work, -3. Let's see if -3 works. So 2 comes down, -6, what's that, 11, -33, 15, -45, yes. Yes, yes, yes. So this one did work, right? -3. That's going to create a factor of what? X plus 3. And then you could continue synthetic division, couldn't you? But now you'd be on this. But what is this going to be? Like 2 what? 2x squared, 11x. So you could maybe use AC method now, or, you know. But what other number works? What else?
-3 works again.
-3 works again. Ah, good. So let me show. If you do -3 again here, because remember I said you had to start again with what you had before, even if it worked? So -3 goes again. Let's put it in here. We have 2, -6, 5, -15, and that gave me 0 here. So this worked also. I know this is very low on the board, I apologize. And what is left down here? This means 2x plus 5, right? So let me put it all together now. Our original function, factors, the first one we had was this one worked, which gives me an x minus 1 as a factor. Then this right here worked, so that gives me an x plus 3 as a factor, right? But then -3 worked again, which gives me another x plus 3. So I can square it. And then the last one that I had down here is the 2x plus 5. So I can put that here. All of these are linear, right? I mean, let's just pause for just a second, okay? Just for a quick second. I know you want to go, I do too. But let's just appreciate something. Just looking back at the original problem. If you've never done anything like this before, and you've done factoring, you've worked with factoring in your life, and you understand factoring can be somewhat of a challenge, but you start to pick it up maybe after time. Just come to appreciate what it is that we are now able to do. I mean, this is a very ugly polynomial, right? If you were asked to factor that the first day you walked in here, say, hey, let's go ahead and factor that, you probably would have gone and dropped the class, right? I mean, you just feel, how the hell are we going to factor that? Well, maybe you're still looking at it right now today. Maybe you still want to drop. But you know what I'm saying? Like, if you have not seen this before, it's the first time you've ever been exposed to it, it's pretty remarkable that we can break this down. It takes a little bit, right? We have to make this list. We have to grind this out a little bit, but there is a way to do it. All right. So we're supposed to set this equal to 0, right? We're still working on x-intercepts. So each one of these gets set equal to 0 to get my zeros. This one is obvious, right? X is what? 1. The next one, we set that x is -3. But this one right here might take a little bit of thought. It means that we have to set that to 0, right? So you move the 5 to the other side, it becomes a -5, and you divide by 2. So -5 halves. Do you understand that this one is not as clean and easy as this one? This one is just the opposite of what you see. Opposite of what you see here, you have to count for the 2. So take the opposite of the 5 and then divide by the 2. So you're solving that equation. Here they are. Now, while we're here in step 2, we're also supposed to talk about crossing and bouncing. So we're supposed to, what's going to happen at 1? We're going to cross through here because the power on the factor is an odd number. At -3, we're going to bounce across. You're not going to bounce across. You're just going to bounce off the x-axis because that's even. And then at -5 halves, you will cross because that power is odd.
Well, I think if you write the equation on that order.
It's okay.
You put the 2x in front of the x squared, the x plus 3 squared.
You put this one in front of this one.
Yeah, when you draw it,
It won't, as long, you have to keep the squared on the x plus 3 because x plus 3 was the one we had twice, right?
Like when you draw it, like so you gotta cross this one, cross this one. Or you can flip it to where you cross, and then bounce.
Well, look, because the crossing goes with the 0. It doesn't go with, it's not going to go with this order. It's the order which they appear on the number line. So when you get to the -5 halves, you will cross at that one. And you will bounce at this one, and you will cross at that one. We're not saying, as you draw it from left to right, you cross, bounce, cross. It's the order in which those numbers appear on the number line. Does that make sense?
Yeah.
Okay. All right, so now the y-intercept. What's the y-intercept? -45? Is that right? F of 0 is -45. And I'm ready to draw. Our x-intercepts are what, -3? -5 halves. What's -5 halves? Where's that? It's 2.5, right? 2.5. -2.5. So here's -2. That's right here. And then our other one is x is 1. Like that. The next thing I draw, my y-intercept, is at -45. So why don't I just count by 5, 10, 15, 20, 25, 30, 35, 40, 45. -45 is my y-intercept. My left and right behavior, up. So far left point, I go up. Far right point, I go up. What am I supposed to do at -3? So go back and look at that. You're supposed to bounce off -3. So as I draw this, I'm going to bounce off -3, come back up. And then I got to get back to this point. And when I get to the one that's -5 halves, right? I'm supposed to cross through.
Yeah.
So I'm going to come up. It doesn't matter how high I come up. I just need to come back down and cross through. And then I've got to get all the way down to my y-intercept and then get all the way back up here and cross. So I'm going to come all the way down here. I'm going to come all the way back up like this. And because that looks weird, doesn't that look kind of weird? Like I'm going up and all of a sudden I joggle to the right. Because I'm writing in pencil and not a pen, I adjust my graph to look smooth. Remember, at the end of the day, your graph must be smooth and curved. You can't have corners, can't have weird jumps. Is it a function, vertical line test? Yes? Okay. Let's take a, well, we don't have time for a quiz, do we? can we talk about our next class at least? Next week's kind of weird. Next Tuesday, we're supposed to cover the next type of function, which is called rational functions. We're supposed to have a review next class. And then next Thursday is a holiday because of July 4th. And then we're supposed to come back from the holiday and have our exam. And I've kind of rethought that. I think it would be better if we'd not had that exam the first day we come back from our holiday. Do you agree? July 4th weekend, you don't want to be sitting there going to have a test when I go back. But that means we'll have to push that test to Thursday, July 10th. Okay? So our plan is next week to finish out 3.5, which will be graphing the rational functions, not polynomial, but rationals. And then we'll have our holiday. We'll come back. We'll have to add some stuff on, and we'll review. So, questions? You need to know what your homework is, right? Let's do this. I gave you homework for page 327. Let me just look at these real quick. Make sure this is what I want. 3.4. Oh, attendance. I gotta pass this out. Okay, please sign in while I get the assignment verified here. 3.4. Okay, it's going to be page 342, 57 through 73 odd. The instructions on those problems say to use the guidelines for graphing polynomial functions to graph. The guidelines that they're talking about are the 4 steps I gave you. This is quite a few problems here, right?
Yeah.
So that's quite a bit of work. But not every single one of them requires synthetic division. Some of them factor nice to begin with. There'll be 4 terms, grouping will work. You know, so you won't have to go through the punishment of synthetic necessarily for every one of them. I do plan on, when we come back on Tuesday, I do want to have a quiz first thing. A quiz on graphing a polynomial function. Because I want to make sure everyone understands that before we move on to rational. Just polynomial. Yep. All right. Okay, that sign-in sheet's getting around. As soon as you sign it, you can go.